Cavity Quantum Electrodynamics Part 2. Optical communications is a vital and important area. One reason for this is that for distances longer than 1 centimeter, the energy needed to transmit a bit using a photon over a fiber is smaller than the energy required to charge a typical 50 ohm electronic transmission line covering the same distance. Similarly, it may be that optical qubits may find a natural home in communication of quantum information, such as in quantum cryptography, rather than in computation. Despite the drawbacks facing optical quantum computer realizations, the theoretical formalism which describes them is absolutely fundamental in all other realizations. We can always design optical quantum computers with different and better kind of nonlinear medium. We've already discussed the formation of optical photon quantum computer. We will begin this presentation by discussing its drawbacks. And in continuation of the previous presentation, we will continue with the design of optical cavity quantum electrodynamics. And this brings us to the drawbacks of the unfeasibility of a single photon quantum computer. Though the single photon qubit is attractive, it suffers from some serious drawbacks. Photons are simple to generate and measure. In the dual rail representation, arbitrary single qubit operations are possible. However, interacting the photons is difficult. The best nonlinear Kerr media are quite weak. They cannot provide a cross-phase modulation of pi essential for the representation of the controlled NOT gate between single photon states. Single atom cavity QED methods. Single atom cavity QED methods offer a potential solution to the dilemma with the one photon quantum computers described previously. Single photons are good carriers of quantum information, but they require some other medium in order to interact with each other. Because they are bulk materials, traditional non-linear optical Kerr media are unsatisfactory in satisfying this need. Isolated atoms and decoherence. However, well-isolated single atoms might not necessarily suffer from the decoherence effects. They could also provide cross-phase modulation between photons. In fact, what if the stage of single photons could be efficiently transferred to and from single atoms whose interactions could be controlled? The main experimental components of cavity QED systems. 1. The electromagnetic cavity. The main interaction involved in cavity QED is the dipolar interaction given by D dot E between the electric dipole D and an electric field E. Whereas for the atom, the electronic energy eigenstates of an atom can be very complicated. But for our purposes, modeling an atom as having only two states is an excellent approximation. This shall form part of the next presentation. The Fabry Perot cavity. In practice, it is difficult to change the size of D, the dipole moment. However, E is experimentally accessible. So a very large electric field can be realized in a narrow band of frequencies and in a small volume of space. And the apparatus that achieves this is the Fabry Perot cavity. The Fabry Perot cavity is basically based upon the Fabry Perot interferometer designed by Charles Fabry and Alfred Perot. The quantum mechanical description of the Fabry Perot cavity is as follows. In approximation, the electric field is monochromatic. It occupies a single spatial mode and can be given by a very simple quantum mechanical expression. E is equal to I epsilon E0 A e to the I k dot r minus A dagger e to the minus I k dot r. A basic component of a Fabry Perot cavity is a partially silvered mirror of which incident light vectors EA and EB partially reflect and partially transmit. They produce output fields E-A and E-B. They are related by unitary transformation given by the matrix E-A, E-B equal to the matrix under root of R, under root of 1 minus R, under root of 1 minus R minus under root of R, EA, EB, where R is the reflectivity of the mirror and location of the negative sign is a convention chosen as given here for convenience. Fabry Perot cavity is made from two plane parallel mirrors of reflectivities R1 and R2 upon which light E in is incident from the outside as shown in the figure. Inside the cavity, light bounces back and forth between two mirrors such that the field acquires a phase shift e to the I phi on each round trip. Phi is a function of the path length and frequency of light. Using the matrix equation for E-A and E-B, the cavity internal field is given by E cav equal to summation over K Ek, which is equal to under root of 1 minus R1 E in divided by 1 plus e to the I phi under root of R1 R2, where E0 is equal to under root of 1 minus R1 E in, Ek is equal to minus e to the I phi under root of R1 R2 Ek minus 1, E out is equal to e to the I phi under root of 1 minus R2, E reflected is equal to under root of R1 E in plus under root of 1 minus R1 under root of R2 e to the I phi E cav. The power in the cavity. One of the most important characteristics of a Fabry Perot cavity for our purpose is the power in the cavity internal field as a function of the input power and field frequency. P cav upon P in is equal to modulus of E cav upon E in raised to the power 2, which is given by 1 minus R1 upon 1 plus e to the I phi under root of R1 R2 the whole square. Now two aspects are noteworthy. First, the frequency selectivity is given by the fact that phi is equal to omega d by c, where d is the mirror separation, c the speed of light, and omega the frequency of the field. Physically, it comes about because of constructive and destructive interference between the cavity field and the front surface reflected light. Second, on resonance, the cavity field achieves a maximum value which is approximately 1 upon 1 minus R times the incident field. And this property is invaluable for cavity QED. This brings us to the end of our second part on cavity QED. I thank you very much for your time, and we will now move on to the next presentation on quantum computers.